Using stochastic interest rate models, we can now price all interest rate derivatives. In the sequel, we will focus on the standard derivatives, interest rate futures, caps and floors, and swaptions. In this first part, we will recap the definition of an interest rate futures contract. We will then derive a formula for the futures rates. As we have seen earlier, futures rates typically differ from forward rates, the difference being called the convexity adjustment. We will now calculate these convexity adjustments for Gaussian Heath-Jerome-Morton models. We will illustrate our results in the Vasicek model. Let us recap what we have learned about interest rate futures. Similar to a forward rate agreement, an interest rate futures contract allows to manage the exposure to the simple spot rate prevailing over a future period T0, T1 with lengths that we denote by delta in the following. Recall that in contrast to forward rate agreements, interest rate futures are daily mark-to-market. The marking-to-market works as follows. At any date small t, the futures price is quoted. It is given in terms of the futures rate as shown here. If the futures price changes from time t to time t plus delta t, the holder of the contract receives a cash flow which is given by the difference of the futures price at time t plus delta t minus the futures price from date t. We denote this cash flow by delta futures price at t plus delta t. This cash flow can be positive or negative. The futures rate determining the futures price is chosen according to the following rules. At the delivery date T0, the futures rate is equal to the underlying, which in this case is the simple spot rate. At any earlier date, small t, the present value of the cash flow from holding the futures contract has to be 0. This is the present value of the cash flow. It has to be 0. We then approximate the discount factor for small delta t by e to the minus rt times delta t. Because this is measurable with respect to the information available at small t, we can pull this out from the expectation, and we are left with a conditional expectation of the cash flow itself. We infer that the conditional expectation has to be 0. But this just means that the futures price process is a martingale under Q. Because the futures rate is linear in the futures price, we conclude that the futures rate process itself is a martingale under Q. Hence, the futures rate at any time small t is given by the conditional expectation under Q of its terminal value, which is the future simple spot rate. Now let us contrast this with what we know for the simple forward rates. We recall that the forward rate process is a martingale under the T1 forward measure. Hence, at any date small t, the simple forward rate is given by the conditional expectation of the future simple spot rate, but under the T1 forward measure. The difference between the futures rate and the forward rate is called the convexity adjustment. we denote it by the letter gamma. This value depends on the underlying interest rate model. We now calculate the convexity adjustment in a Gaussian Heath-Jerome-Morton model. Consider a Gaussian Heath-Jerome-Morton model with a deterministic forward rate volatility sigma. As usual, we denote the T-bond return volatility by the letter V. It is minus the integral of sigma. Some stochastic calculus then shows that we can express the T0 bond price divided by the T1 bond price as shown here. This is the product of a Q martingale times a deterministic function of time. From this we easily infer that the conditional expectation of the terminal value of this ratio process, shown here, is given by the ratio process itself at time small t times this deterministic correction factor. Notice that this identity holds because V is a deterministic function. Using this identity, we can now calculate the convexity adjustment as shown on the next slide. The convexity adjustment gamma is the difference between the futures rate minus the forward rate. Using the identity from the previous slide, we can calculate this conditional expectation. Plugging that in and rearranging terms, we arrive at this expression for the convexity adjustment in a Gaussian Heath-Jerome-Morton model. Notice that the convexity adjustment gamma is non-negative if the exponent is non-negative, and this holds in particular if the cross products of the sigma are non-negative. This is clearly the case in a one-factor Vasicek short rate model. Recall that the Vasicek short rate model is a Gaussian Heath-Jerome-Morton model with this volatility function. We now compute the convexity adjustment for the parameters as shown here. For the futures and forward rates written on a 3 months simple spot rate. The plot on the left-hand side shows the convexity adjustment as a function of time to maturity. We see in this example that the convexity adjustment is smaller than a basis point for times to maturity up to 5 years. In the right figure, we see the convexity adjustment as a function of varying volatility parameter sigma. Here we fix the time to maturity to be 6 months, and we vary the volatility sigma from 0 to 2%. As we can see, the convexity adjustment is increasing in sigma, and the order of magnitude is again somewhere between 0 and 1 basis point.